One of the useful concepts when we're looking at electromagnetism or gravity is the idea of a field. We started off last semester when we looked at little g for gravity. That's actually a field. And for the first few weeks, or a month or two, depending, we treated it as a uniform field, meaning it has the same magnitude and direction everywhere. In reality, that's not really exactly right because we know the direction changes. Things fall towards the Earth's center, so if we moved from Savannah to Los Angeles, there would be a significant difference in the direction to the Earth's center. The field strength also changes in magnitude as we move away from the planet, so it would be a little bit weaker at the top of a skyscraper than it would be at the bottom. The field works as kind of a placeholder and lets us talk about what the force on a mass would be even if we didn't have a mass there. It was force per unit mass, and that's the same thing as an acceleration, and that's why we used it in the very beginning of class. For electrostatics, we can define an electric field E, and we want the force per unit of what responds to that force, which in this case is charge, so our units for the electric field will be newtons per coulomb. We can look at the gravitational example again to see how we would find this electric field. In the gravitational case, G is big F over m, so we put big G m1 m2 over r squared divided by one of those masses. That gives us, for the gravitational field of the other mass, gm over r squared. We can do the same thing with Coulomb's law when we look at the field of one of these charges and the other one is in that field. So the field of Q1 and Q2 is feeling it, we would take Coulomb's law, divide by the charge on Q2, and we get kq over r squared. This is the form for the electric field of a point charge. This points radially outward in every direction, or for a negative charge, radially inward from every direction. This works for a point charge. It turns out it also works if you have a spherically symmetric charge distribution. We get the same restriction for gravity, but it turns out we don't really have to worry about it for gravity because anything that's only held together by gravity will compact itself into a sphere anyway. Anything big enough for a real field will compact itself into a sphere. That's why the moon, the planets, the sun, they're all approximately spheres. The only differences you see, things like asteroids are so tiny, they're held together by the same electrostatic forces that hold rocks on Earth together, and that's why they can have any shape in particular. Now, E is a vector field, which means it has a direction as well as a magnitude at every point in space. We define the E field to point outward from positive charges and into negative charges. The reason we do this is if we then put a positive charge in that E field, it'll move downstream since the force on it will be in the same direction as the field. That means a positive charge will move away from another positive charge and towards a negative charge. A negative charge would of course go in the other direction, just like helium balloons move up when we let them go and rocks move down. We can imagine putting a bunch of charges together in such a way as to produce a uniform field. This would have the same magnitude and direction of everywhere. That's what we treated Earth's field as. So, in this approximation, you could imagine this is our ground. It's perfectly flat. We have two what are called plumb lines, where basically you just hang a weight from a string and look at which way it points. It'll always point to the center of the Earth. For a uniform field, these two lines are perfectly parallel. They both point in the exact same direction. Also, if the field is uniform, it's the same strength wherever we are. So this scale holding this purple mass reads exactly the same thing here as it does higher up. Now, the Earth doesn't really work like that. If we want to blow it up to a large scale, it's a little bit easier to see. Here, when we're far away on the scale the size of the Earth, there is a big difference between the weight that this mass would feel and the weight that this mass would feel. We can see as we move away from Earth, it's going to get less and less significant, the pull of gravity on it. And these two plumb lines are really pointing towards the center of the Earth. And if we're very far away from each other, opposite sides of North America, for example, these directions are very different. So this is different than what we're used to. We didn't have to worry about it with gravity because we really only had the one giant source of gravitational field, which is the Earth, and we don't generally move on distance scales that are large compared with that. So a charge in a uniform E field acts just like the masses acted in Physics 1, which means you can use kinematic equations to connect the position, velocity, and acceleration of a charge released in this field as a function of time. As a practical matter, if we wanted to actually make one of these fields, what we would do is get two conducting plates near each other to make kind of a sandwich with a gap between them. We put positive charges on one plate, negative on the other. As long as we stay away from the edges of the plates, so it looks like we're in the middle of two infinite planes, we'll see that the field looks pretty uniform to us. The device that we make when we do this is called a capacitor, and we'll definitely do more with those.